Welcome! These videos were recorded while I taught topics in econometrics over Zoom, but they were edited so that the student faces, their questions, and my answers to those questions do not appear. That explains why you may notice some unnatural transitions and why the videos are shorter than a normal lecture. But hopefully you will enjoy them anyway. Bye now. Um, we are starting the second part of this course, and it's just gonna be on ways to do asymptotic approximations in a way. It used to be I used to, there were some quarters where I spent like 7 or 8 lectures on this, and we would include things like large deviations and limits of experiments and a variety of other things. But depending on the quarter, I sometimes cover more or less because I want to cover other topics. So this year in particular is going to be sort of like a shorter version, but it's going to have the fundamentals. So we're going to talk about local asymptotics today. Then we're going to talk about contiguity the following class. Then we're going to talk about local asymptotic normality and then convolution theorems. And hopefully, this is going to give us a quick overview of one way to think about local approximations or asymptotic approximations, broadly defined, um, for inference and estimation when we get to convolution theorems. So today we're starting with this. All right. So the setup that we're going to discuss is going to be generic, and very quickly we're going to move to an example. And the reason that I'm going to go through an example today, and actually for most of this second part, is because a lot of the issues that come when you start teaching local approximations in general context is that you have to introduce a lot of notation and sometimes explain how we do certain expansions and things that are not particularly difficult, but they just get in the way of trying to get the main intuition out of things. And my goal is not to give you the tools so that you can go and actually develop these techniques in your own paper. It's just that I want you to understand conceptually how to interpret these techniques, what's their value, and not the mechanics behind them. So if tomorrow you want to do econometric theory and you need to do these things, I'm assuming that you're just going to go to certain references that are in the syllabus or that we can talk after class, and then you can learn the mechanics by yourself. Okay, but what matters is understanding um, w- what's their potential usefulness or not. And to those of you that do not care about doing econometric theory, I want you to understand the scope and the limitation of this type of approximations. Okay. All right. So, what's a generic testing problem? We're gonna observe some data, xi. That let's start again. We're gonna observe some data. Then I'm gonna denote by xi. It's gonna be IID with some distribution p, and p is gonna belong to a family of distributions that I'm gonna denote by bold p, which is gonna be in turn indexed by a finite dimensional parameter theta. Okay. And so then we want to test whether theta belongs to some subset of its parameter space that I'm going to denote by capital theta naught versus the alternative that theta belongs to capital theta 1, which is going to be an alternative. In principle, theta 1 and theta 2 should form a partition of the parameter space theta. We're going to test this hypothesis by using a test function, which I'm going to denote by phi n. And it's just going to be a function of the data that returns the probability of rejecting the null hypothesis after observing the data. An example that we're very familiar with is whenever phi is an indicator function that a certain test statistic that we're going to denote by Tn exceeds some critical value that we're going to denote Cn 1 minus alpha, where alpha is going to be the nominal level of our test. The definition of pointwise asymptotically level alpha, which is the one that we actually saw in Econ 480, is that the test says pointwise asymptotic level alpha if the lim sup of the rejection probability or the expected value of this test does not exceed alpha for any theta in the null hypothesis. And then we know the test to satisfy this requirement include wall tests, quasi-likelihood ratio tests, Lagrange multipliers, and the like. So the question is, if we have two different tests for the same null hypothesis, I'm going to call them phi1 and phi2 n, and both are pointwise asymptotically level alpha, how can we choose between these two tests? What are the considerations that we can take into account to select, say, phi1 over phi2 or the other way around? And today we're going to study this question in the context of one really old semi-parametric model, which is the symmetric location model, which goes as follows. Here, p theta is a distribution with density f of x minus theta on the real line. Okay. And so we're going to assume that f is symmetric about 0. And then 2, its median. 0 is unique. So if f is symmetric about 0, then f of x minus theta is symmetric about theta. And so this is a symmetric location model where the parameter that we're going to be trying to do inference on is going to be theta, which is the location of the symmetric distribution. So when you take expectations with respect to p theta of the random variable x, well, the mean is going to be theta, and the median is going to be theta as well. The final piece of our assumptions is going to be that the variance of p0 is going to be positive and finite. So I'm going to denote this by sigma squared 0. It's going to be the integral of x squared f dx, and this is going to be between 0 and infinity. The testing problem that we're going to consider is we're going to test that theta is 0 versus the alternative that theta is positive. So it's just going to be one-sided, because that way, again, this is another simplification because we can just ignore absolute values and the like. And the question is how we can test this null hypothesis. And what we're going to do today is we're going to propose two such or different tests for this type of null hypothesis in this particular setting. And then we're going to compare their properties and using some different types of approximation techniques. Any questions about the setting? All right. SLM here stands for symmetric location model. We are going to start with the t-test. The t-test, which is going to be over phi1 n, just going to be the indicator that square root n x bar n divided by sigma hat n is greater than z1 minus alpha, where c1 minus alpha is the 1 minus alpha quantile of a standard normal. So here we have that x bar n is just the sample average of our observations, and then sigma hat n square is just the sample variance. And then, as I said, z1 minus alpha is a 1 minus alpha quantile of a normal 0, 1. And then under the null hypothesis, we claim that this test is pointwise asymptotically level alpha. So to do this, we compute the expected value under the null of this test, which is just the probability under the null that square root n x bar divided by sigma hat n is greater than, z1 minus alpha. And then we recall here that since we have an ID sequence of random variables with finite second moments, we have this conversion distribution to a normal 0, 1 as n goes to infinity. So this converges to 1 minus the CDF normal, which is equal to alpha. So the fact that the t-test is pointwise asymptotically level alpha, which again is something that we argue in 480 in a slightly different context, in this case is just straightforward. Okay, theta is IID, find mean variance, CLT applies, and then by using this particular critical value, we have that the test satisfies this property. The other test that we're going to consider is the so-called sign test, okay, which is also a very old test in statistics. And what this does is think about in the following way, which is the 2 here is a normalization, you'll see in a minute why, but you have 1 over square root n, the sum of the indicator that these random variables are positive minus a half. And so the idea, if this distribution, it's truly symmetric around 0, then roughly you should have half of the observations above 0, half of the observations below 0. So you're just going to count how many are above 0 relative to a half. And so in order to study the properties of the sign test, we will always start by looking at the mean and variance of this object over here, which is our random variable in a way. So under the null, the expected value under the null is 0 of the indicator that xi is positive. Well, it's just the probability that xi is positive, and it's just going to be 1 minus f of 0, where here capital F is the CDF of the density that we described before. And then in turn, the variance of this random variable, well, the variance under the null is quite simple because this variable is Bernoulli with probability 1 minus f. So it's just p times 1 minus p. Notice that this here under the null is 1/2, and this here under the null is 1 over 4. Because under the null, the distribution is symmetric at 0, right? And so f of 0 is a half. Then we have that by the CLT, one over square root n, sum from 1 to n of the indicator that xi is greater than or equal to 0, minus its mean, which is a half, converges in distribution to a normal with mean 0 and variance 1/4. And now you see why we have these 2 over here, because if you just take the 1/4, as a square root divided by 1/2, then you have the 2 on top. And so, in other words, 2 over square root n, sum from 1 to n of this, converges in distribution to a normal 0, 1. So then the expected value under the null of this second test, phi 2n, which is the probability under the null, 2 over square root n, sum from 1 to n of our indicator that the variables are positive minus a half greater than z1 minus alpha converges to 1 minus the CDF z1 minus alpha, which is alpha. So the t-test is pointwise asymptotically level alpha. The sign test is pointwise asymptotically level alpha. And so in principle, you can use either one to test the null hypothesis that we want, okay? But today, it's more about trying to think about how we can compare these two, given that we know that both satisfy this, let's call it a minimal requirement of controlling the rejection probability in the limit. So, as I wrote here, it's natural to base comparisons of two different tests in terms of their power functions. And, all of you probably knew this already when I started thinking how we can compare things. So, what's a power function? The power function, we're going to denote it by pi n theta. It's just going to be the expected value of the test under theta. It's the probability of rejecting the null hypothesis as the function of the unknown parameter theta. If you pick theta under the null, it's just going to be bounded by alpha. We know that. But if you pick a theta under the alternative, we don't know what could happen with this rejection probability yet. So, but in principle, this, of course, is going to be a different number depending on the value of theta. And in principle, also, we have to face the challenge that this function, okay, for a given sample size, it is typically an object that is unknown. Even in the setting that we are studying right now, which is very simplified. It's a symmetric location model, as it's a scalar x. We have a lot of structure. Yet, it is often the case that it is difficult to compare finite sample power functions because we don't have much to say about these finite sample power functions. Of course, there are settings where this is not the case. Suppose you're in a parametric context where you can compute these probabilities. That'll be great. But in our setting, and in many of the settings that we have to deal with in econometrics in general, we do not know the power function in finite samples. Since we don't know this, we're going to try to do so in some asymptotic sense. Okay, we're going to just try to take n to infinity and then see if we can make a comparison. But one thing that I want to emphasize, and I'm going to keep emphasizing in this class as we move along, is that the goal is always to say something about the finite sample power function. So we're going to be doing a lot of things to do this. And there are multiple ways to say something about an object that you don't know. But what I don't want you to get confused is that the goal is never to say stuff about the things that we'll be able to compute. It's not that we suddenly will care about these asymptotic objects because they're interesting by themselves. They are interesting provided they provide a good approximation to the objects that we really care about, which in our case here is always the finite sample power. Okay? If we knew pi n theta, then we wouldn't need any asymptotic approximation. Okay? We'll just use pi n theta. We don't, we need to rely on some sort of approximation. So that's what we're going to do next. We're going to try to approximate this pi n theta with some, again, in some asymptotic sense. And we're going to start with something that I'm calling here a naive approach, which already tells you that probably is not going to work. Okay? So what is the naive approach? Well, give me the power function, which is here. Okay? And let me just see how this behaves as n tends to infinity. Okay, that looks simple enough. The problem is that this expectation, or the probability, is according to the distribution p theta. Okay, so in our notation, e theta is expectation with respect to p theta. That is, when x has distribution p theta. And then we need to think about what it means. So to model this easily, I'm going to use a property of the symmetric location model that, as I said, happens to be convenient, simplifies a lot of the algebra, which is I'm going to introduce this random variable yi as xi minus theta. And guess what? This random variable has distribution p0 when x has distribution p theta. You're recentering. Okay, so if you recenter x by theta, of course, the recenter version has location at 0. Okay, and so then I'm going to use two tricks, which is first to know that y bar n is, of course, x bar n minus theta. We're going to use that. And then the other one that is more subtle, but still clean, is a sigma hat square n, which we define as 1 over n, the sum from 1 to n of xi minus x bar n square. Well, we just move the location. So if you add and subtract theta inside, this is exactly the same as this. So the sample variance of this random variable x's is exactly the same as the sample variances of these random variables y's. So now I can study the power function, because then I want to say pi 1 n of theta is the probability under theta, and this is the t-test, right, of square root n x bar n divided by sigma hat n greater than z1 minus alpha. What I'm going to do is I'm going to replace x bar plus as y bar plus theta. So now this is the probability under the null, p theta, p0, okay, of the square root, y bar n divided by sigma hat plus square root n theta divided by sigma hat n. So here I use our connection between y bar and x bar given here. I just replace x bar. Now I'm going to take this to the other side. And again, one point that matters is that when I replace x with y, I replace that in the numerator and in the denominator as well, because we just show here that the denominator, is exactly the same for x's and the y's. So, but what matters now is that this object over here is just a function of y's. It's not a function of x. And on this end, we don't have any type of random variable. So this guy converges in distribution to a normal 0, 1 under p0. And this guy over here diverges to negative infinity. So you put all together, this converges to 1. Importantly, we could analyze the behavior of the test under the alternative, any given theta that you give me, by computing probabilities under the null only, by just doing this trick where we replace x by y. And so that's nice, because then we know stuff about p0 like this. And so then we can transform this problem into a problem of how p0 behaves in the limit. And since this is diversion, then the power goes to 1. What we learn is that you give me an alternative and the power of the t-test asymptotically goes to 1. So now let's just think about the sign test. Perhaps I should have written the sign test here, but remember that the sign test is the indicator, the 2 over square root n sum from 1 to n of the indicator that xi is positive minus a half greater than z 1 minus alpha. And so first thing is that I want whoopsie. I want the behavior under b theta. So first, I always said, like, when analyzing this case, we need to just look at the mean and variance. So what is the expected value under theta of this indicator that x is greater than 0? Well, I'm going to say if you subtract theta from both sides, this is the expected value under the null of the indicator that yi is greater than minus theta. Right? Because I just subtracted minus theta from both sides. And then I said y is equal to x minus theta. Remember, I'm going to write this mapping here. It's right here. And so now this is 1 minus f of negative theta, right? Because this is the distribution under the null, and f, we said, is the CDF of f, little f. So that's the case. Okay, fine. This is no longer a half because we don't know what theta is. It could be anything that is not 0. Let's look at the variance. Well, the variance is always easy because it's the variance of a Bernoulli random variable. And we know already p. So this is p times 1 minus p. So it's going to be f negative theta times 1 minus f negative theta. So we have a random variable right now that is not centered at a half. It's centered at this point. And it doesn't have a variance that is equal to 1/4. It's equal to this number over here. So what I want to do in a way is to rewrite this object first so that it is properly centered. Okay? So how do we make sure that the object is properly centered? We're just going to add and subtract the right mean so that we can get the object that we want. So let me define, Sn, which is the statistic of the sign test, as 2 square root n sum from 1 to n indicator xi is greater than 0 minus a half. And then what I'm going to do is I'm going to add and subtract the true mean inside. So it's just going to be 2 square root n sum indicator xi is greater than 0. Let's subtract the mean first. Let's add the mean again. And let's put back the 1/2 that we had before. So now this is going to be 2 times 1 over square root n sum from 1 to n of the indicator x greater than 0 minus its mean, which is 1 minus f at negative theta. And then I'm going to have the other part, which is 2 as just going to be square root n because nothing here depends on I of 1 minus f negative theta minus a half. This guy over here, I'm going to call Sn of theta. And this guy over here, notice that you can write it as just 1/2 minus f negative theta. Importantly, by the CLT Sn theta converging distribution to a normal with mean 0 and variance f negative theta 1 minus f negative theta. Okay, haven't done much yet. I just said now I want to analyze this sign test, and I need to analyze the behavior of the sign test under the alternative hypothesis. Well, first thing you want is some object that you can say what's going on asymptotically under p theta. And then that's something actually I should have clarified. This is under p theta. Okay? Under distribution p theta, that convergence happens. And now we have this equation over here that gives us a relationship between the statistic that we have, the sign test statistic, and something that we know and some extra factor that is going to be floating around. That's where we are. Here I'm just repeating what I just wrote. Okay? So now let's study the sign test. So pi 2n theta is expected value under theta of this test. And this is the probability under theta that Sn is greater than z 1 minus alpha. Well, this is the probability under theta, and I'm going to use this relationship that we wrote here on top, is Sn theta plus 2 square root n 1/2 minus f negative theta greater than 1 minus alpha. Where recall that I'm calling this object over here Sn theta. Just taking this to the other side, I have Sn theta greater than the quantile minus 2 square root n 1/2 f negative theta. So this guy, conversion distribution to a normal with mean 0 and some variance under p theta. Just said that in the previous slide. And then this guy, all that term diverges to negative infinity. Why? Because, well, 1/2 is greater than f negative theta because theta is positive and f is symmetric. Okay, at 0, this f. And so this is less than a half. F at 0 is a half. F negative 0 is less than a half. So you put all this together, this diverges to 1. As n goes to infinity, of course. So the sign test was slightly more annoying than the t-test, but still like relatively easy to analyze. Only required to add and subtract things. And the main takeaway is that now we learn that both tests have power functions that go to 1 as n goes to infinity. So if you just compare, let's say, asymptotic power, you have to conclude that these two are exactly the same. Okay? Both are local, pointwise asymptotically local level alpha under the null, and then under the alternative, it doesn't matter which alternative because we didn't specify that, it's just theta. Then both will have a power function that will just go to 1. They look alike. So, questions? Okay, let's keep going. Now, I wrote here this. Let me just go through this. There are many ways, or there are a large number of ways of embedding our situation with a sample size This was a disaster. So there are innumerable number of ways of embedding our situation with a sample size n in a sequence of hypothetical situations with a sample size larger than n. And this is, something that we need to sort of like keep in mind. What we really care about is the finite sample behavior of the power function, what I call pi n of theta, and not really some limiting object. The idea of the limiting object is to approximate the object we care about. In our sample size of size n, we know that the power is not 1, okay? Less so uniformly over all the thetas in the alternative. It may be very close to 1 for thetas that are far from 0, but for thetas that are close to 0, we would expect the finite sample power function to be less than 1. And so here, you have the actual power function for some sample size. Doesn't matter what sample size, but this is the power function. And then we have the t-test, the sign test, and the Wilcoxon sign rank test that we're going to see later in class. And so what you see is that here's the null. X here is theta, okay? So this would be theta in our notation. And so what you see is that, this is 1. No, when theta is very far from the null, well, the power functions do look like 1, okay? And when theta is very close to the null, the power functions are really far from 1, okay? So we have a power approximation that looks like this. Let me choose some elegant color. That's our approximation. Alpha under the null, 1 under any alternative. Like if you just plot your approximation, it looks like this. And that's the approximation that we got for these power functions that are over here. So what is this approximation saying? Well, it's just saying the following. It's like if you take the t-test, which has this power curve here, and then suppose that you increase the sample size. Let's say that this curve here for the t-test is n equal to 100. Okay, well, suppose now that you just have n equal to 1,000. Well, n equal to 1,000 then will look like this. And suppose then that you have n equals to whatever, 10,000. Just going to look like that. And all that our power approximation is doing is that if you just fix a value of theta here, it's just saying as n increases, you're going to go to 1. That's all it's saying. Sure. And the t-test and the sign test have this property. Okay, sometimes this property is called consistent in power, just saying as n goes to infinity, the power approaches 1. But then if you just view it as an approximation of the power curve, it's just naive because it's just giving us alpha here, 1 over here, and both tests will have this property. Then we can see, if you just look at this picture, there are differences in finite samples, okay, that this approximation is not capturing. So as an approximation of what's going on in finite samples, if we were in a situation in which we couldn't simulate well, then, this would not give us things that are really useful. In general, it doesn't ever give us anything that is very useful. However, when we look at this picture, we look at the power curve looks like this in this case, right? And so regardless of the actual shape, we see that the power is like close to alpha when you're close to the null, close to 1 where you're far from the null. And the question is, what do we mean by far and close in general? And can we do an approximation that captures this, that captures the fact that what it means to be close and far from the null? And that's what we're going to try to do. So this leads us to local asymptotic power. A local asymptotic approximation considers the behavior of the power function evaluated as a sequence of alternatives that we're going to know by theta n, where theta n tends to 0, the null, at some rate. This provides a local to the null asymptotic approximation to the power function. In a way, another way to say this is that when we did the naive approximation, we let n go to infinity. n going to infinity says that eventually we have a lot of information. We know everything because we have a huge sample size. And then when you have a huge sample size, you can always tell the difference between, a null and an alternative because, you know everything. And so the problem with that asymptotic approximation is that it's just making the problem easier, easier, easier as n goes to infinity, whereas the difficulty of the testing problem stays constant. And so the approximation that we're going to try to do now, and this is one of the ways of doing it, is like as you let the sample size increase, you want to make your testing problem more complicated. And if you have this balance in which the more information you gather goes at the same rate, if you want, as the more complicated the problem is becoming, then you can capture what's going on in finite sample in which you're not perfect. You're just going to have a limited sample size to make an assessment about a particular question, a testing problem, or something like that. So here it says if theta n tends to 0, really slow, well, that is going to be the same as just considering a fixed theta, because then the power is going to go to 1. You can let theta move, but the power is going to go to 1. But if theta n goes to 0 too quickly, you just take a sequence that is really fast, well, that is going to be the same as if you are at 0. Okay, so you're just going to reject with probability alpha. So if it goes too fast, you get alpha. If it goes too slow, you get 1. So what's the magic number? Well, it turns out that, I wrote here there's a delicate rate in between these two extremes, such that if theta n tends to 0 at this rate, then the power will tend to a limit in alpha comma 1. And this rate may be different in different problems, but in problems such as the one that we are considering here that are so-called smooth, okay, the rate is just 1 over square root n. So the sequence that we're going to consider are theta n that are equal to some number h divided by square root n. Later in class, we're going to introduce other notions of defining what it means for two probability measures to be close to each other. And one of such notions is going to be the notion of contiguity. And then we're going to see that for this type of problems, what makes two distributions close to each other is just going to be related to 1 over n. And we're going to be able to get this rate from the definition of contiguity. For now, you just have to believe me that in a way, if heuristically, if you understand the rate at which your test statistic or your estimator is learning, okay, in this case, we're using sample averages, for example, and we know that the rate of convergence of sample averages is 1 over square root n. Well, that's the rate that we want to use to balance. If we were using non-parametric estimators, and so we will be convergence at a non-parametric rate, say like nh to some power or something like that, then that is the rate that you will want to consider. And in other settings, if you had a faster rate or any other different rate, then you always want this theta n to go at the rate at which you're learning. We're going to see other examples as we move on. But for now, this is the exercise that we want to do. Now we want to rephrase everything we did. Now we want to look at the power function, but instead of looking at the power function at a specific fixed value of theta, now I want to look at the behavior of the power function along this sequence of parameters, or sometimes called sequence of alternative hypotheses. Let's start with the t-test. Well, the t-test is always very simple. So that's the cool feature of working with the t-test. Now, what we have is that x is IID with distribution p theta n. Notice how the distribution now changes with n. And when are we using this trick where y, which is xin minus theta n, has distribution p0. This is great. This makes the t-test really easy to evaluate because regardless of whether you have this distribution that is changing with n, okay, yn has the same distribution for all n. This is sometimes called a triangular array because if you write it, like this, you say n is equal to 1, then you have x 1, 1. Then this has distribution p1. And then when you have a sample size of 2, you have x 1, 2, x 2, 2. These are IID p2. And then you have n3, you have x1, 3, x2, 3, x3, 3. Then these are IID p3. And then you see how it looks like a triangle. that is just coming down like this. Okay, and that's why that's called a triangular array. So then note, I want to say here, we still have y bar and n equals x bar and n minus theta n, and then sigma hat and n square is, I'm going to write here same for xin and yin. So it doesn't matter. The sample variance of x's and the y's is exactly the same. We're only changing the location. That's all we're changing. So now let's consider the behavior of the power function. Pi1 n at theta n is the probability under p theta n that square root n x bar and n divided by sigma hat and n is greater than z 1 minus alpha. And then this is the probability under the null now that square root n y bar and n sigma hat and n plus square root n theta n divided by sigma hat and n is greater than z 1 minus alpha. And I'm going to take this to the other side. And notice here, I'm going to write h divided by sigma hat and n, because square root n times theta n is equal to h. Recall from the previous slide that we defined theta n as h divided by square root n. So now this converges to 1 minus the CDF of a normal at z 1 minus alpha minus h divided by sigma naught. I'm going to say again here because, whoops, sigma hat and n square converges in probability under p naught to sigma square, right? And then of course square root n y bar and n divided by sigma hat and n converges in distribution to a normal 0, 1 under p naught. And now we have a number that is in between alpha whenever h is not 0 and 1 whenever h is not too big. Okay? And so this is a function of h. And h is known as the local parameter. Of course, you don't care about h per se. H doesn't have any meaning by itself. Just that suppose that you care about theta, the alternative 1.5, and then you know that n is whatever 300 in your application. That means that, you know, with this function, you will just set h to 1.5 times square root of 300, and that's the h that will give you information. I will try to approximate the power function at 1.5 given your sample size of 300. Okay, so that's sort of like the use of this. And but leaving that aside, then we have this approximation to the power curve now as a function of the local parameter h. And there's a one-to-one mapping, of course, between the local parameter and the parameter that we care about. So not surprisingly, you're going to see that often the plots of the local power functions are plotted as a function of the local parameter. Okay. Questions about this? Now we're going to look at the sign test. And, the sign test always more complicated than the t-test. We want to start by looking at the behavior of this type of sample average, okay, under the distribution p theta n. So we can say the following. First, we don't need to do everything again. We know that the expected value under theta n of the indicator, the xin, is greater than 0. It's just going to be, again, 1 minus f, now evaluated at negative theta n. So that's that. And then the variance of this indicator is, again, p times 1 minus p, f, negative theta n. Oh my God, come on. 1 minus f, negative theta n. And then our previous result, we know that Sn, which is the sign test statistic, was twice Sn theta n plus twice square root n 1/2 minus f negative theta n. We had that before. And Sn theta n was 1 over square root n, sum from 1 to n of the indicator that x is greater than 0 minus the mean, which is here 1 minus f negative theta n. What we want to claim, or what we need, is to say that Sn theta n converges in distribution to some normal with mean 0 and b under p theta n. And this is the first aspect that becomes more complicated in the sign test, because in the t-test, we got around this issue by replacing the y's. We just had to deal with p naught, okay? But now we don't get around it. We just have something that is properly centered, like here is, for every theta n is centered at the right place. But now the problem is that this distribution is changing with n, and then the usual CLT doesn't apply. So what we need is a CLT that allows us to deal with this sequence of distribution. And so one of such CLTs is the Lindbergh-Feller CLT. So one version of that is the following. For each n, let z and I from 1 to n be IID with distribution Pn. Notice that here we're allowing the distribution to change with n. And we're going to suppose that this random variable Zn is properly centered for every n. The expected value of this is 0. And we're going to assume that the variance of this random variable, which may change with n, is finite for all n. And then we have the Lindbergh-Feller condition, which in this case can be written as the limit as n goes to infinity of 1 over sigma squared n of the expectation according to Pn of Zn squared times the indicator that the absolute value of Zn exceeds epsilon square root n times sigma n is 0 for any epsilon that we plug in here. And then if we have this, this, and this, we have a result that says square root n, the average, divided by this square root of the variance, conversion distribution to a normal under this sequence of distributions Pn. And as I wrote here, what we would like to assert is that this type of CLT can be applied to this object that we have over here. So in our case, notice the following. In this notation, we're going to say Zin is just going to be the object that we have here inside. So it's just going to be the indicator of this. minus this. That's our random variable. And then in this context, sigma n square we saw before is f negative theta n 1 minus f negative theta. So now we want to apply this CLT to this test statistic. And in order to do so, we realize that our test statistic is just the average of this guy. So this is our Z. And what's the variance of Z? Well, it's the variance of this indicator, which we already showed in the previous slide, that is f times 1 minus f. So that's what we should do. It's actually quite straightforward to check this condition here, because the expected value of 0, well, we know the expected value of 0 is properly centered. That the variance is finite, yeah, of course. This guy is bounded actually by a fourth, right? So we know that this guy is less than or equal than 1/4, okay? Because, the worst that could happen is that f is a half in both cases, and it gives us a fourth. It's like the usual p times 1 minus p. And so then the thing is, how do we check this condition that we need for the CLT to apply? Well, let's do so. Again, the CLT states that this is exactly what we want. Okay, if we have this tail condition, we're going to use Z as here and sigma over here. So first, I'll say no. Since this is the sequence theta n that is converging to 0, okay, we have that f of negative theta n is converges to f of 0, which is a half. So there exists some delta such that sigma n squared is greater than or equal to delta for all n greater than or equal than some capital N. That is, sigma squared n is bounded from below, right? So it cannot be arbitrarily close to the minute that n is large enough, because, theta is converged to 0, and so f is converging to a half, and then sigma is just f times 1 minus f. So that's what we have. And so then, you realize here that the limit of this n going to infinity of our here term, that is 1 over sigma n square expected value of C and I times this indicator, then we have that this is 0 because sigma n is bounded from below for n large. So this denominator here doesn't bother us because sigma n is less than or equal than 1/4. Okay. So it's not too big, which, doesn't complicate this term over here. And then we have that Z and I is in between 0 and 1 because it's just an indicator minus 1 minus a CDF. And the CDF is in between 0 and 1. So then eventually this indicator here cannot happen because for any epsilon that we pick that is positive, and sigma square is bounded from below as well, so it's just going to be positive, okay, then square root n eventually is going to make this number large, okay, and this indicator is just going to be 0, okay. So great, we have that. Now in our notation, we have that Sn theta n divided by the square root of f negative theta n 1 minus f negative theta n, converging distribution to a normal 0, 1 under p theta n. But in fact, what happens is that 2 times Sn theta n also converges to in distribution to a normal 0, 1 under p theta n, because square root of f negative theta n 1 minus f negative theta n converges to 1/2, because theta n is going to 0. Actually, this is just a deterministic convergence. Whoops. Okay, we are almost there. But are we all good now? So now we are here. Local power of the sign test. We have, this is our connection between the sign test statistic and the remaining objects. And then we just show that 2 times Sn theta n, which you can write like this, converges to a normal. And now we're ready. Pi 2n theta n, which is the probability under theta n that Sn is greater than z1 minus alpha, is equal to the probability under theta n that 2Sn theta n is greater than z1 minus alpha minus 2 square root n 1/2 f theta n. Oh, there's a typo here. Look at that. This should be a theta n. Okay. So now this converges to 1 minus the CDF of a normal, because we know that this guy over here converges in distribution to a normal 0, 1 of z1 minus alpha. And now the question is, where is this going? Okay, so let me do that on the side here. Notice that I'm saying note f of negative theta n. If you just do a Taylor expansion of this function at theta n at 0, so around 0, then it's going to be f0 minus theta n times the density of f whatever at 0 plus a term that is just little o theta n. And so if you just take now this to the other side, or the other way, sorry, let's just take this to the other side and this guy's to the other side, then what you have is that square root n f0 minus f negative theta n is just square root n theta n f naught plus little o1. And this is a half. And this is equal to h times f of 0 plus little o1. So we conclude then that this expression over here converges to h times the density at 0. And so this is 2 times h, the density at 0. And we have the local power function of the sign test. Which again, even though we haven't done any manipulation that was sophisticated in any means, it shows you how to do the power calculations in local approximations. The minute that the model starts being more sophisticated, it starts to have this type of issues that the sign test illustrates in a very simple context. So here are the two power functions. This is the local approximation, the local power function of the t-test. This is the local power function of the sign test. They both look the same. Both are 1 minus the CDF of a normal. Okay, because we're using at some point some form of CLT, which gives us asymptotic normality. They both have the same quantile here, but they differ in what multiplies the non-centrality parameter or the local parameter h. Okay, and in particular, as I wrote here, if 2 times the density at 0 is greater than 1 over sigma naught, okay, the sign test will be preferred to the t-test in a local asymptotic power sense. Okay, this is just saying, look, the higher this number, the higher the power is. And so since both are being multiplied by h, when this number is greater than this number, which is 2f0 is greater than 1 over sigma 0, then sign test is going to do better. Then think about it. In the normal case, if you're dealing with normal distributions belong to the family of symmetric location models. Then if f is the density of a normal, then we know that the t-test should be the uniformly most powerful for testing the null hypothesis. That's a finite sample result. So it would be weird if we have a property in finite samples that then when we do our approximations, the approximations don't capture. Well, it turns out if you plug in the standard normal density f here, that will show up here, and the connection to this sigma over here, we find that this is actually the case. If you just plug in normality, this power curve dominates this other one over here, is above. Okay. So if you instead consider distributions that have fat tails, think about Laplace or any other distribution that have fatter tails than the normal, the situation is reversed. And the sign test has better power than the t-test. So what's the moral of the story is that if the underlying distribution is symmetric, then the t-test, while preferred for many distributions, is not as robust as the sign test for distributions that have fat tails. And the reason should be kind of like straightforward, because you see that while the t-test is taking averages of the x's while taking into account the magnitude of those observations as 1 over n, the sum of xi's, the sign test doesn't take into account the magnitude. It only counts how many are to the right and how many are to the left. Okay, so if suddenly you have distributions that give you really high values with some probabilities, okay, then sign test doesn't really care. As long as it's to the right or to the left, it's all that cares about. So when you take the ratio of these numbers multiplying the local parameter, you get something that is called asymptotic relative efficiency. And so the asymptotic relative efficiency of the sign test relative to the t-test takes this formula over here. Okay, it's 2f divided by 1 over sigma square, which just gives you 4f square sigma square. And so if you ever hear the term asymptotic relative efficiency, it just means, taking the ratio of this constants multiplying h in the derivation. Questions? So let's keep going and let's talk about these caveats that I just mentioned. I call it here limits of local power approximations. We just derived these two functions. And then if you just look at these functions and you plot them, you'll notice that the local power function is monotonic and has essentially the same shape as the power function in a normal location model. And again, why is this? Because it follows from CLT's type of arguments. However, the accuracy of the approximation can be poor at non-local alternative. Like, it's funny because even though in the name, we have the word local, okay? You would be surprised how often people forget that this is something that is approximating something locally. Otherwise, it would be called power approximation. But, this is something that is supposed to work well, or is intended to work well for values of theta that are close to the null. Why? Well, because that's how we did the approximation. We took a theta n going to 0, right? That's what we did. So, and so that's what we're supposed to be approximating. So, however, people will extrapolate. Okay, so you have this normal thing, and now you want to say something about the power far from zero. So like, well, I have a function. This function, you can evaluate this function close to zero, far from zero. Why not? And then you just extrapolate. And so the problem here is that there was a series of papers, both one by Nelson and Sabin, and the other one by Sabin and Wurst. I don't know how you pronounce this. Probably not that like that, but apologies. Um, Sabin was a colleague of Joel Horowitz at some point in time. And so, where they try to just bring this discussion of the limits of the local power, and what they notice is that when you have power functions that are non monotonic, okay, so I wrote here, if the finite sample power curve is non monotone, then the asymptotic local power approximation will be poor at non local alternatives, okay? When the true power function is monotonic, typically these local approximations work well, in close to the null and far from the null. But the question is, what happens where there's non-monotonicity? So as I said, there are a series of papers. The first one, which is the one that I'm going to present now because it's very short, okay, and so it's easy to see. It shows how the non-monotonicity brings problems. But the problem with this paper is that some people criticize it as being a model that it was just a toy model, not very relevant for applied work or for econometrics in general. And the second one essentially fixed that because they consider just a probit model. And the second paper essentially shows that you have this type of non-monotonicity in very standard testing problems that you usually do in the context of binary choice models. Okay, logit, probit, doesn't matter, just binary choice. Okay, so this will take an entire class to do. We're not going to do it this year, but I'm going to talk about this first paper, explain what's the intuition behind the non-monotonicity problem, and then I want to briefly mention what's the takeaway from this second paper later. So, non-monotonicity of the t-test. We're going to consider this problem where P belongs to a family of distributions that are indexed by parameter theta. And look at this. The family of distributions has to be normals with mean exponent of theta, comma 1. Okay, and then what we want to test is whether theta is 0 versus the alternative that theta is negative. So notice how we introduce a nonlinearity here artificially, right? It's like here you can write E of theta. It's just kind of like weird because you can call this mu and then everything. It's even a normal model, right? And so, but we introduce a nonlinearity artificially in the simplest way possible, which is just do e to the power theta. And so you can think about as say a linear regression model, a nonlinear regression model where y or x is an exponent of some variables multiplied by some coefficients plus an error term, type models like this, exist. But then we're not going to think about this more sophisticated thing because you can get the same result. Where today we're just going to focus on testing this simple problem where you get draws from a normal, but for whatever reason you care about theta when the mean is e to the power theta. Again, why? Because we're trying to introduce nonlinearities in the simplest way possible. So I wrote here for simplicity of exposition, focus on the scalar case, psi with distribution P as above, and you wish to test whether this is equal to some theta or not, which is, say, going to be 0 later. All right, this is a parametric model, so we can do log likelihood. Look, the log likelihood is this, there's a constant, and then the term that usually arises in the normal case. Then the score is just going to be the derivative of this with respect to theta, which is just this without the square times the exponent. Okay, and the Hessian is just going to be the second derivative, take another derivative, and then you just get a 2 over here. The Fisher information is just going to be the negative of the expected value of the Hessian. And then remember, the expected value of this x is e to the theta. So you have e to the theta minus 2 e to the theta is just going to be negative e to the theta. And then since you have a negative here, they cancel out. This is e to the theta square. Okay? And what's the MLE? Well, the MLE will set the score to 0. So the MLE of theta is just the log of the sample mean. So all very standard. So now let me write the t-statistic, and notice how this is unusual, but I want to do this. I'm going to view the t-statistic as a function of the theta hat that you obtain. Okay, I'm writing the t-statistic as a function of the point estimators that you of theta that you have. So it's going to be negative square root n theta hat minus theta naught divided by the square root of the efficient information. Now we know what the efficient information is. The square root is just going to be this exponent. Okay, so the t-statistic is square root n theta naught minus theta hat times the exponent of theta hat. Remember that this negative here, just we use it to flip the order of theta naught and theta hat. So, and this is the formula that I want. This is the t-statistic. It depends on theta hat. Okay, and we're testing theta naught versus theta less than theta naught. Okay, are we good? Up to here, just very standard parametric. Just write the t-test. Well, look, this is what happens. This is the t-test, okay? The t-statistic is a non-monotonic function of theta hat. And if you just complete the derivative is square root n, the exponent, times theta naught minus theta hat minus 1, okay? So it has a maximum value at this point that happens at theta hat equals theta naught minus 1. So if you look at this red picture here, this is a t-statistic. At 0 is 0, so don't look at the to the right of 0, we don't care. But then to the left of 0, it goes up, reaches the maximum, and then it starts going down. Okay? And so what we're going to do now is to think, okay, so what's the rejection rule? Well, the rejection rule is just going to be that this statistic is going to be greater than something. Let me just... That's awful, but well, that's the line that I got. And so we just look at, when this is going to reject. Well, it's going to reject when the t-statistic exceeds the critical value. Okay? But there are two crossing points here. This and this. Okay? So, but then look at this. Suggests that for any sample size, the more negative the estimate of theta is, the less likely the null hypothesis will be rejected. So consider your estimator. If your theta hat is 0, you're not going to reject. Your theta hat is negative. At some point, you cross your threshold, whatever is the critical value you're considering, okay? And then you're going to reject. But now you're more and more negative, and then you stop rejecting. And this is the t-test. So what's the power function? Well, the power function is the probability that the t-statistic exceeds some critical value, okay? And so if you just look at this picture over here, you can define this as some theta L and some theta H here, the intersection of those points. And then it's just going to be the probability that theta is in between these points, okay? Theta L and theta H. And so, then you can take the exponent and, this will be x bar. So you can compute this probability. So you can make under the null this equal to alpha. It doesn't matter what it is. And then you're going to have the exact power. You can compute the exact power, and the exact power looks like this dotted thing that is over here. The power, as you move away from 0, goes up, 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 up. And then after a certain point, it starts going down, 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 down. And then you do the local approximation, and there's this red line that we have over here. It goes up like this, because the normal approximation looks like the power curve, in a normal location model. So what do you see here? Well, notice that when you focus on thetas that are close to the null, the local approximation is actually quite good. Okay? You see how the red and the circles are close to each other. You can even extend this up to here if you want. Well, that's very good. But then when you really extrapolate far from the null, the local approximation could be awful. Here you have 0.38, and here you have 1. So we have 60%, or 60 points, okay? Difference between what the approximation tells you and what's going on. And so um, here I just this is a very short paper. It was published in Econometrica. Okay, as simple as it is, because it brought up an important point, which is how non-monotonicity of power functions, okay, presented a challenge for this local approximation. Okay, but the the moral is that this is the case. Of course, this is something that doesn't happen for all test statistic or all tests in general, because if you go back to the previous slide, this dotted line here was the likelihood ratio test. And you see how the likelihood ratio test doesn't suffer from this non-monotonicity. It's just a problem in this case of the wall test or the t-test, okay? It's not that this testing problem is difficult all the time. It's just that this choice of tests, a t-test or a wall test, was a bad choice in this nonlinear setting. So, any questions about this? Okay, so one thing with this example, and again, the reason why at some point, you know, I think this paper is beautiful, and I think the main message is actually very clean. Not to make a big deal about it, but just to um, have a better understanding of the scope and limitations of things like a local asymptotic approximation. But it was initially probably criticized on the grounds that, you know what, who cares about this model, right? So it's just the e to the theta. Who knows that this holds in other type of nonlinear models? Um, it's not always the case that the or that a non-monotonic test statistic will lead to a non-monotonic power function. So which is something that then could remove concerns, and so that's why later on it came this paper that it was about binary choice models. Okay, that I'm not going to present this year, but it's a 99 paper, also published in Econometrica. And then what this paper showed, okay, was that if you had a binary choice model, and by that I mean, imagine that if you have a model where the probability that yi is equal to 1, conditional on x being equal to little x, and then you assume that that is f, I don't know, x prime beta with f known. So this includes, again, logit, probit, and so on. And then any null hypothesis that would be, suppose that, to make it simple, let's assume the beta is just beta 1, beta 2, okay? Any null hypothesis that was like beta 2 is equal to something, I don't know, 2, versus the alternative that beta 2 is not 2. Well, this is, even though people often will refer to this as a simple null hypothesis, right? Because just beta is equal to something. This is composite because beta 1 is free. I'm not saying anything about beta 1. Okay, it's just beta 1 could be anything. When you test one component, you're just letting the other components be free. Well, what this paper shows is that in this type of testing problems, in nonlinear and binary choice models like this, where f is known, which again includes logit and probit, okay, and you care about testing the hypothesis that one slope is equal to something and the other ones are not, and so on, then they show that the power goes to 0 along this particular ray. And so what that means is that the power function, if you just plot now beta 2, will just is alpha here, and then because whatever beta 2 is 0 stays in all, it just goes like this, and then it goes like this. So it's not monotonic. So again, if it's not monotonic, you know that the local power approximation is going to be really far from the null, because the local power approximation is going to be monotonic. Okay? And the result applies to any non-randomized test with size less than 1 and is derived for a finite sample. Okay, so for every n, you're going to have this non-monotonicity. So this paper, even though it's kind of like, is really clever in terms of the arguments, and that's why I used to teach it, but it doesn't offer you any skills that will probably apply beyond this paper, but it's really clever. It's not sophisticated. It doesn't use any math that is complicated. but it has a very powerful result. So, and it gives a setting in which you can say happens in practice. You use binary choice models, you test one component, and then one case in which you know that you will have non-monotonic power functions. And then as a result, where the local power approximations will not be good far from the null. Having said all this, and as I said at the beginning, local power functions are dominant in theoretical analysis, comparisons of tests, and so on. And they still are today, not because they are not subject to criticisms, partly because that's sort of like, as I said, they're convenient from a manipulation point of view, that we know we have the theory to work out a lot of different or analyze a lot of different settings. But in the cases that they work poorly, there are other types of approximations. But as I said, other type of approximations also have their own probably separate limitations. And the main takeaway that I want to take, that is not the negative that we just see now, is that, and we're gonna keep talking about this as we move forward in the class, is that sometimes when people that were non-econometricians, some as a applied researcher, whatever, looks at somebody presenting a theoretical result, and then they're letting some parameters move with n, the immediate reaction is like, oh, that's weird and you're cheating or something like that. Okay, it's like as if like it is convenient for you to move n or let move things move with n, and that shouldn't be the concern. The concern is whether whatever things are moving with n, what are they trying to capture? And in our context, was this idea that thetas that are close to the null, okay, tend to be harder to detect in finite samples because we look at the finite sample power curves. And so that's why we consider alternatives that were under the null. And despite the limitations of this local power, we know that the local power presumably gives us a reasonably good approximation, at least close to the null. And for sure is a lot better than the naive approximation that we did at the beginning, where we just took n to infinity and we let everything be fixed, okay? Which in principle looks, if you want, more natural, but it leads to significantly worse approximations, okay? So that's the things that you have to have in mind, which is always what's the best approximation. And the best approximations are often the ones that have at least some features of the model or some parts of the distributions that generate the data moving with n. Okay. And so that is it for today. Next class, we're going to start talking about contiguity. So now I'm going to move to questions.